Hi everyone, I will present the result and discussion. I will move to the result first. To have a big vision, I will zoom it to the result first. Here we can see that uh, I denoted X as a number of student car accidents per day, and I tabulate the data accordingly. And the first step, I calculate the mean, where summation of fx divided by the summation of frequencies, uh, and I have 1.8822. Next, I calculate standard deviation, where square root of summation fs squared divided by f minus b bar x squared, and I got 1.664. To get the variance, I just square it, I get 2.769. Next, since the parameter lambda is an unknown, the sample mean is an unbiased estimate of the population mean. That is lambda equals to bar x equals to 1.822. A goodness of fit test will be carried out to test the sample data by using Poisson distribution with lambda equals to 1.822 at 90% significant level. As I denoted X as number of students car accident per day, H naught will be the number of students car accident per day has a Poisson distribution with lambda equals to 1.822, while H1 or alternative H, the number of students car accident per day does not have a Poisson distribution with lambda equals to 1.882. We assume under H naught uh, it follows the Poisson distribution with lambda equals to 1.822. We calculate the probability of Poisson distribution, and the probability of Poisson for 0, s equals 0 is 0.1526, while 1, 0.2780, and so on. Then we calculate EI. EI equals to observed frequency multiply multiply with the probability. And total observed frequency is 45, that's by probability, and we got 6.8670 for x equals 0, while x equals to 1, 12.5100, and so on. Next, uh, next, in the second slide, we can see that there are three expected frequency fall below 5. The value was combined with the adjacent value together, and the following result shown in the result. As we can see above that with x equals to 6, 5, and 4, the I value is less than 5. So what we do is we combine it together and make sure it is greater than 5. Next, we calculate the degree of freedom. Since the parameter lambda is estimated, and this is case 2, then we use the formula V equals to K minus 1 equals to 3. Then at 90% significant level with the degree of freedom 3, the critical value is 0.584. The critical value was obtained by using the chi-square distribution table. Then the condition where if the chi-square statistic is greater than 0.584, we reject H naught. The following table is a form to calculate the value of chi-square statistic. And as we know, the formula is summation of observed frequency minus estimated frequency. We square it divided by estimated frequency, and we calculate for all the x values, and we have 5.2360. We sum up all, and the claim or the final part where we can see that 5.2360 is greater than 0.584. Thus, it falls in the critical region. At 90% significant level, we do have sufficient evidence to reject H naught, and we conclude that the number of students car accident per day does not follow Poisson distribution with mean lambda equals to 1.822. Then We can then I move to the discussion. For the discussion, we can see that from our observation, the data I collected does not follow Poisson distribution. From our calculation, the sample mean was 1.822. Variance is 2.768, while standard deviation is 1.664. The requirement of data to follow the Poisson distribution, variance of a Poisson random variable is equal to lambda. Since the variance of the number of students car accident per day is almost 2 times estimate lambda, then we can say that the data does not follow the Poisson distribution. Next, we encounter situation where the rate of accident may not be constant. The rate of car accident may be not be constant over the 45 days period. It was like fluctuating due to the various factors that affected. For example, maybe the condition weather, time of day, or changes of traffic pattern. I will take some example where there were heavy rains and flood in the Pago and Mua area can causes accidents. Another example, if parking is limited in college, students who double park their car easily get into accidents. So the data that I collected was less accurate, plus the students who illegally bring their car without having proper driving license, training and less experience causes accidents too. So this might be one of the factors why the data does not follow the Poisson distribution. In other hand, from our observation, the number of students car accident per day are actually dependent on the situation of the students. But for the Poisson to assume that the data is follow the Poisson distribution, the events are independent of each other. However, in this case, students car accident, there are many certain factors that increase like the likelihood of an accident occurring. For example, if a student has had a previous accident, they may they may be not likely to have another accident in the future. This means that the number of accidents one day may be dependent on the number of accidents on previous day, which will violate the independence assumption of the Poisson distribution. Similarly, students who get in accident are more preferable to use buses arranged by the university to go to campus or student grab, as they are very safe for them and it's very cheaper too. So these factors are likely to cause the number of students car accident to vary over time and not follow a Poisson distribution. So I can conclude that for a Poisson distribution, the evil occur independently, but they are not actually. Next, we look at the significant level of bonus fit test where we fix to the 90% because to avoid type 2 error, where accept the false null hypothesis, where H0 is accepted and H1 is rejected, yet in reality is not true. In order to prevent this, as far as possible, any false claim from happening, the significant level is fixed to 90%. However, the higher a significant level is the most tolerant of a type of error exists and more likely where to reject the null hypothesis by mistake. But nothing to worry because not all cases of type 1 error will exist. Since in our case, it doesn't follow the Poisson distribution from the observation we have proven just now. Finally, the critical value obtained by using the chi-square distribution table actually depended on the degree of freedom and significant level. Normally, if the population parameter lambda is given, we use formula uh, lambda is given. If the population parameter lambda is given, uh, we will calculate the uh, Poisson probability. Unless if they doesn't provide, then we use the formula bar x to calculate estimate mean. Some sample statistic parameter lambda need to be computed by estimating, as I said just now. For example, at 90% significant level, 5 categories with parameter lambda are estimated. Degree of freedom and the critical value will be 0.584. I repeat again, Here we use case 2 to find the degree of freedom, where since we are estimating the bar x, we use v equals to k minus m minus 1. Since we estimated one parameter, then we minus with 1. However, at the same significant level, with 5 categories with population parameter lambda is given, degree of freedom and the critical value will be 1.064. This implies that the critical value dependent on the degree of freedom. Although the claim is true, we state that the student's car accident is becoming worse, but the distribution cannot be modeled by the Poisson distribution. Next, I move to the simple linear regression method, where I generated from using Excel. A simple linear regression is statistically technique used to find relationship between variable and predict future values. Uh, as we can see, the regression statistic, the correlation of coefficient known as a multiple R, how strongly two variables are correlated linearly. It is absolute value, which ranges from -1 to 1, and then the R square coefficient of determination is a measure of fit quality in range from 0 to 1, with a value around 1 suggesting the model fit the data well. For instance, the X failure account for 0.46 or 46% of the y-axis, while standard error depicts the precision regression analysis, and the value is on the regression statistic table. Next, B naught is 12.107 and B1 equals to -1.893. Hence, we get the equation where y equals to -1.893x plus 12.107 will be our regression equation. And that's all. Thank you.